Good morning, everyone. My name is Stefano Fasciani, and the title of my thesis that I'm defending today is Voice Control Interface for Digital Musical Instrument. I'll start the presentation talking about the publication related to this thesis. I published 4 conference papers in 2 NIME, 1 ICMC, and 1 DFX conferences covering different aspects of this thesis, of this work. 1 journal article published in eContact, which provide a more user perspective and performance perspective of using this system. And another journal article is under preparation, which provide a more generic overview of the whole system. Then I've been presenting, demonstrating, and using this system in a variety of places, including conferences, symposium, and guest lectures. Next, I'm going to talk about the context of this research work, the motivation, and the aim. Digital musical instruments are composed by 2 main parts, the musical interface and the sound generation. These 2 components are totally independent and they can be physically separated. The musical interface has a central role because it captures a musical intention of the performer, which is expressed through a body gesture, and it translates this information for the sound generating part. In certain musical contexts, there is a bottleneck, there is a limitation between gesture and musical interface, because although a single interface or multiple interfaces may expose a large amount of instrument parameters, the number of parameters that a single performer can control simultaneously is still very limited. So this problem, it has been known since pretty long time, and it has been addressed by different approaches. One approach is using machine as a co-player. So I pre-program some action on a machine and then the machine play along with me. Divergent mapping, so controlling more musical parameters with one control dimension. Another approach, much more interesting and relevant to this thesis, is the one of the augmented instrument, where the designer of the interface identify and exploits spare bandwidth of the performer. So in this figure, for instance, there's a trumpet where there is some button on the finger rest. So the finger that is not used for playing is a spare bandwidth, and it can be used for allocating extra musical control task. So this is the same approach that more or less I'm taking in my work. So using voice to provide an extra musical control layer. Voice is often a spare bandwidth in several performance contests. And voice and body gesture can be used simultaneously without require particular training or particular high cognitive attention, and they provide completely independent information. In my thesis, I reviewed the literature extensively, and I analyzed all the work that has been proposed in the past, in which the designer or the researcher provide different methodologies, different approach to establish the relationship between voice and digital musical instrument. Those based on explicit mapping were pretty simple system, fixed, not adaptable to the specific performing condition, and they were in a certain way less interesting than those based on generative mapping. Generative mapping means that the mapping is not defined by the instrument designer, but is defined by an algorithm, which is usually based on machine learning techniques. This second category of work presented limitation as well. In particular, most of the work, they failed to adapt to the different characteristic of voice of different performers. They require a complex procedure or a lot of training data for setting up the system, and the sonic output of the instrument, target of the control, is usually not considered in the loop that generate the mapping. So I address all these limitations in my thesis, defining a set of design principles that I follow in conceptualizing my work. In particular, I wanted to provide a system to control an arbitrary number of instrument continuous value parameters driven by the instantaneous variation of the voice timbre. I wanted the mapping to be adaptive in the direction of the voice of the performer and in the direction of the sound generated from the instrument. And I want the mapping to be generated unsupervisedly in order to minimize the expertise and the effort of the user in setting up the interface. So next I'm gonna go into the core of this presentation, talking about the method, the main challenges, the way I address this with my design. This is a scheme that can be applied to any musical interface. There are 3 main blocks: gestural data acquisition, gestural controller, and mapping part. I break down the problem of mapping the voice to instrument into these 3 blocks, and I'm going to analyze one by one in this presentation. But first, I introduced 2 concepts that are important in order to understand how this interface works. The concept of vocal posture and vocal gesture. A vocal posture is a voice timbre that do not change over time, and here we have an example. And as a design specification, if the voice timbre does not change, the instrument parameters should not change as well. While a vocal gesture is an arbitrary variation of the voice timbre over time. And here we get another example. This is a simple gliding between different vowels. And as another design specification, when the voice changes, instrument parameters somehow are supposed to change. In analyzing the gesture, I do not consider the temporal unfolding of the gesture. I'm more interested in analyzing the spatial unfolding of this gesture. So to understand how the voice can represent a high-dimensional control space. Next, I'll talk about the gestural data acquisition. So the first question I have to answer is once I capture the voice from a microphone and I have it in my digital domain, what to do with the voice. So which feature should I compute and which parameters should I use to compute this feature in order to achieve this mapping task. And most of related work provide a fixed answer. In my case, I wanted to provide an optimal answer. Optimal in terms of the specific voice of the performer and the specific gesture we want to use to interact with the instrument. As a training data, the user is supposed to provide a set of vocal postures and few examples of the vocal gesture you want to use to interact with the system. So over the vocal posture, I compute a very large set of low-level features, including LPC, PLP, and MFCC. And on every single feature, I go and measure the relative mean difference, which is a sort of like measurement of the noisiness of the feature over the posture. Those that are too noisy get discarded because not compliant with the design specification. So from this stage, I get a selection mask to select only the robust feature. Next, I compute the features over the vocal gesture. And in this case, I compute the intrinsic dimensionality, which is a sort of estimation of the amount of non-redundant information embedded in the vocal gesture. I combine these two into a quality rating, in which the intrinsic dimensionality has a larger impact. I repeat this measurement, changing the setting to compute the features. And I select setting that maximize this quality rating. Here we have 3 examples, 3 plots, where the top black line is this quality rating. Very similar gestures and posture provided by 3 different users, and as you can see, the maximum is different for every user. So I get this case-specific optimal setting to compute and select the low-level feature to use in this mapping in this mapping task. So next, I have defined how to compute my sensor data. Usually, I got a number of signals coming out that is above 10, so let's say between 10 and 15. And next, the gestural controller has the role of pre-processing this data. So producing in output a lower number of parameters, but much more representative of the control intention of the performer. So next, I compute the low-level feature over the whole vocal gesture provided as a training data. And let's suppose that the dimensionality is 2 because it's easier to represent it on screen. I reduce the dimensionality. Any technique I use to reduce the dimensionality, I always have the same problem that I'm going to describe next. Most of related work use the dimensionality reduction as a gestural controller. And one of the problems is that there will be always, whatever linear transformation I apply to this space, empty regions. That means given the vocal gesture, the region will be never reachable. I will never get sample in those positions. Which means in the output of the gestural controller, I will have a limited possible combination of these 2 signals. I address this problem proposing to apply a conversion of the coordinate system. So I want to change a coordinate system. And to do this, I use the self-organizing map in a very non-conventional way. So the self-organizing map provides me a representation of the high-dimensional vocal data into a lattice structure. And as the output of the gestural controller, I can use the relative index in the lattice structure of the closer node related to the high-dimensional space. I can apply this methodology in 2D, in 3D, and even in a higher number of dimensions. This is an example of the train SOM. So you can see that this lattice, the relative position in this lattice will be my new coordinate system, which actually equally span between the two coordinates. The problem of doing this are several. Whenever I train an SOM, I got folding, twisting, discontinuities, and topology distortion. Taking the most easier example to describe the problem, the twisting, for a monotonic gesture that goes from bottom left to top right, I will have a monotonic output on one axis and a non-monotonic output on the other axis. So the output will go up and down. And this is a sort of inconsistency of the way the gestural controller responds related to the input gesture. Another problem is that anytime I train the SOM, I got different results. There's many reasons that generate this problem. One is the dualistic role of an SOM, which reduces the dimensionality, but at the same time it tries to preserve the topology between input and output space, and the completely randomization of the initialization of the weights and the training procedure. I address this problem with my methodology that I call self-organizing gesture, in which at first I introduce a prior step of dimensionality reduction. In this case I'm using isomap, which is a nonlinear technique. And I reduce the dimensionality to M, which is already the dimensionality of the output of the gestural controller. So I free the SOM from the task of reducing dimensionality. Now let's stick to the 2D case example. Next I'll go and find what I define the gestural extrema. So in a simple way, they are the four most far apart points within this training data set. And how I use it? Then I use it for training my SOM. And in particular, I initialize the weights of the four vertices in 2D at the position of the gestural extrema. And then I modified the training algorithm, modifying the weight updates rule, modifying the random sample points are picked, in order to kind of like apply some force that pull the SOM vertices in the direction of the gestural extrema during the training. Here there is a video of a real training case in which you can actually get the feeling that there is something pulling the SOM from the vertices in the direction of the extrema. So I don't get folding, twisting, and the training is very repeatable. This is in 2D, while this is in 3D. So you can see the 8 vertices initialized at the position of the 8 gestural extrema detected in the data. And this is the final structure that I get, which is a 3D lattice with no folding, twisting, or topology distortion. How to use this as a gestural controller? I repeat the same sequence of operation that I defined here during the training, during the description of the training part, and my voice will be a coordinate into this lattice. And as output, as I said before, I take either the relative index of the closer node, or to increase the resolution of the output, I do indirect distance weighting as a sort of like spatial interpolation. And as a search space, I can either search across the whole SOM, or I can shrink the search to the Moore neighborhood. So it will be in 2D will be 9 points that are the red one that you can see on the slides. Reducing the search to the Moore neighborhood, it provides more smooth and continuous output within the gestural controller output space. As an alternative, I also propose to replace the isomap with a multi-class LDA, which allows the user to define a set of postures that can be directly associated with the corners, so with the vertices of the SOM and with the corners of the gestural controller output space. I evaluated this methodology, measuring how many times I get topology distortion between my method and the standard SOM method, and I got a drastic reduction. Measuring also the repeatability of the SOM that I get after training, and I get a drastic increase. Then I compare my gestural controller with another 4 gestural controller proposed in literature. I just emulated them, and I took 5 different measurements over a simulated use using real data, and I always got best result or results very close to the absolute best. And you can appreciate this visually in this figure. So on the left, in red, there is the second best gestural controller. The blue one is my gestural controller, and you can see as the samples, the output samples and the output trajectories are much more spread in the gestural controller output space. So I don't have any more regions that are not reachable. Here we get a little demonstration of this. So you will hear the voice timbre changing. You will see here into this square this yellow point moving, and actually this one is the output of my gestural controller while here I get my node of the SOM, and you can see the voice vector moving, and the another point chasing it, which is the actual output of the SOM. So the voice is changing, the output of the gestural controller is changing, the instantaneous voice vector is changing, and the other point is actually chasing it, because it's forced to move only one step at a time. Here you have the variation with LDA, where specific postures are associated to the corner, and here at the end there's a search that is not constrained to the neighborhood. So you can see that the transitions are more rapid but less smooth in the output space of the gestural controller. So I've discussed now how to get these up to 3 parameters from the gestural controller. The same methodology can be applied to a higher number of dimensions. I never go over 3 because it's difficult to control a 4D space by voice, and it's also difficult to provide an easy way to represent graphically this space that the user may use to get familiar with the system. So I set the limit to 3, which is already an improvement because I can control up to 3 extra parameters by voice. But in this work, I want to be able to control ideally an unlimited number of parameters. On the top of this, I wanted also to provide a more natural way to interact with the instrument. Whenever we produce voice, vocal sound, we think about sound. We do not think about the movement that we have to do with the vocal apparatus. And the same approach I wanted to take to control instruments. So I wanted to control directly the sound of an instrument, not the parameters of an instrument. So instead of establishing a relationship between the gesture and the parameters, I want to establish a relationship with my mapping between gesture and sound, in particular perceptual aspect of the sound. This is not new, it has been proposed in the past, but I wanted to push this approach a little bit further, making it compatible and applicable to any real deterministic digital musical instrument, not only to few cases. And I want my method to provide a minimum loss, or actually a lossless, few to many mapping technique, which actually provide a dimensionality reduction of the control space. And on the top of this, this methodology would also provide a linear response between gesture and output sound. In order to do this, I still need to know which is the relationship between parameters and sound, which I suppose that is not given to me, so I have to proceed and measure it. So this is the second part of the training of the system, and as a training data, the user has to provide the instrument he wants to control and the parameters he wants to control by voice. Then I proceed to do my analysis, trying all the unique combination of instrument parameters, generating the sound, analyzing the sound, computing perceptual related features, and storing everything into another matrix. I end this procedure with 2 matrices, I and D, which fully characterize the relationship parameter to sound for any given instrument. Within doing this analysis, there are different instruments that may need a different strategy to run the analysis and the post-processing of the data that I measure. So in this thesis, I introduce a taxonomy, so a classification that can be applied to any deterministic musical instrument, and I end up with 6 categories. And for each category, I define a specific way to run the analysis and to do the post-processing of the data. After the post-processing, I have a high-dimensional sonic space. Once again, I reduce the dimensionality either to 2 or 3 dimensions using isomap. Here we have 6 examples, and you can see that case by case, instrument by instrument, the density, the shape, and the distribution are completely arbitrary. So if we imagine to establish the interaction within this space, I will have 2 problems, similar to what I discussed before for the voice. There will be empty region that will be non-responsive, and 2 dense region that will be over-responsive. I address this problem reorganizing the data into this space, preserving the neighborhood between points into the sonic space. And in particular, I did this using an iterative algorithm based on the Delaunay triangulation that relocate the points. And here there is an animation of this algorithm. This algorithm has been proposed and used in the past. I just applied some little modification to avoid non-preservation of the neighborhood that can happen at the border, especially when there are a lot of points. So after this, I got my sonic space organized into a uniformly distributed cube, in this case. I learned the inverse of this transformation with a neural network. And this is the model I learned with a neural network. Then I suppose that, as we discussed before, that my gestural input will be any coordinate into a 2D or 3D space, so a 2D square or 3D cube. And now, I translate, I go into another coordinate system, the coordinate system of the sonic space, using the neural network. And doing this, I will have no more over-responsive or under-responsive region. Every point in the sonic space was generated by a unique combination of instrument parameters, which I can retrieve and use to drive in real time the instrument. The problem of this approach is that the relationship between parameters and sound may be not one-to-one. So very different combination of parameters may generate identical or very similar sound. This is a problem because especially if there is spatial interpolation, temporal interpolation, as I have in my case, in generating the parameter, I may generate discontinuities or wrong parameters, so wrong sounds that are not coherent with a specific position in sonic space. This is an intrinsic problem that it can be really solved and is very instrument dependent. So I address it proposing to search only within a subspace of the sonic space of any given instrument. And this subspace is defined within a neighborhood of my actual sound, but the neighborhood is defined not in the sonic space but in the related parameter space. So you can see here that the green points represent 3 different sizes of this neighborhood, but they actually the points are not really neighbor into the sonic space, are neighbor into another space. And selecting the radius, the dimension of this neighborhood, is a trade-off between what I define the sonic space explorability and the output parameters continuity. So the larger the search space, the easier will be to browse this, the easier will be the larger the neighborhood radius, the easier will be to browse the space, but I will get some discontinuities. The smaller I get it, it would be very difficult to browse the space. I can get trapped in some position, and some other sonic entry into that space may be impossible to reach. I took a set of measurements to evaluate this mapping methodology that I proposed. I took measurements over 34 cases in which I used 14 state-of-the-art digital musical instruments. And one of the measurements, okay, in this plot each line represents one of the different cases, so results are very case dependent. Here you can see that the number of combinations that I managed to obtain is always above 90%, most of the time above 90%, so I got below 10% in most of the cases, in most of the case below 90% of sonic loss. And then here in the bottom plot you can see how the explorability of the space, so how many parameters I can retrieve, changing the neighborhood radius, it increased, but it also increased the potential discontinuities of the generated parameter. So this is a trade-off. And here there's another video. In this video you will see that the output of the gestural controller space, that is still this yellow circle here, is driven by my mouse. So I'm moving the mouse to control this point. This coordinate is transformed into a coordinate of the sonic space through the neural network. And then you will see okay, let's move here. Okay. You will see that there's something moving. So the neighborhood is updated at every iteration. The red point represents the currently selected output. So I'm moving into the gestural controller space, I'm browsing the sonic space pretty uniformly, and in this case I'm driving 1, 2, 3, 4 parameters of the instrument. So I get a 4:2 dimensionality reduction of the control space. Next I'm going to talk about the prototype and the user evaluation. So this scheme summarized the whole approach of my system to control instrument by voice. Learning part very well separated from the runtime part, and within the learning part, the training part of the voice and the training part of the instrument are very well separated and also independent. The same is true for the runtime part, in which the two section gestural controller and mapping part are independent one from each other. Within the prototype, I also implemented a note generator that just look at energy, pitch, and onset detection from the voice, which are characteristic of the voice, not used for mapping purposes. So in this case, optionally, the user can also trigger the sound of the instrument other than controlling the parameters of an instrument just by voice. This is the logical flow of the mapping. So from the voice, I compute the feature, I reduce the dimensionality, and I get a coordinate. I use the lattice of the SOM to translate the coordinate into this intermediate space that is the ideal uniformly distributed square or cube, in which I do a one-to-one mapping between gestural controller and mapping block. And then with a neural network, I change the coordinate again to get a point into the sonic space of the instrument, in which I do my search and I retrieve the instrument parameters. These three representations are provided to the user as a visual feedback. The user never specified explicitly the relationship between timbre of the voice and timbre of the instrument. So the user, when the mapping is ready, the user needs to get familiar with it. You need to figure out what the mapping implemented in terms of like voice to instrument relationship. And these three visual feedback are essential in order to learn to use the system and also to perform sometime. The prototype is implemented in Max, Max for Live, and MATLAB. Most of the training part is implemented in a set of scripts running in MATLAB, while the runtime part is implemented in Max, that is this patch on the top, and here I have the real-time voice analysis and the GUI to control the whole system. Then there are two parallel jobs running in MATLAB. One implements the gestural controller, the other implements the DMI mapping, and then these communicate with instruments that are hosted in Ableton Live, which is a commercial and popular digital audio workstation. And this communication is allowed by some Max for Live device that I developed for this purpose. Communication within this block is implemented in OSC, which is a network protocol, which allow me also to distribute the implementation of this system over different machines running within the same network. And this project has been published as an open source software in GitHub. Moreover, here you can see in the GUI of the runtime part, there are plenty of options that are especially related to this section that the user can choose. So the user can slightly tune the mapping to make it more compliant with his needs or with his desired way to interact with the instrument. And when the options there are changed, the response is immediate. So there is no need to retrain the system. I evaluated this interface, inviting 10 experienced performers familiar with digital musical instruments to evaluate my system, to try my system. At first, I got an interview with them in which we discussed about their profile as performer, to understand the instrumentation they use, the limitation they experience in their own performing context. Then I explained them the voice control interface system. They train the system using their voice, and they start to practice with it. After I asked them to perform a set of use cases. After, I got a second interview in which we focused mostly on benefit and shortcoming of the voice control interface. The profile of the participants were very different in terms of age, instrument they use, cultural background, expertise, performance practices, and exposure to music technology. From a qualitative analysis of the open-end interview, I understand that, I figure out that all participants demonstrated a very well understanding about how the system is set up, how the system works, and how the system can be used. When talking about the benefits, the response were very uniform. They all mentioned the high expressivity, the wide sonic range, the intuitive and natural control, the extra control dimension, and the low application constraints. While when talking about drawback and limitation, the response, the answer were much more variegated and sometimes also contrasting. But most of them, they mentioned the difficulties in tuning the system because there were probably too many options on the GUI, and the name of these options were not really meaningful to them. All the participants said that the visual feedback were essential to getting familiar with the unsupervised generated mapping and also to perform with the system. And 2/3 of the participants said that while performing, while using this interface, the parameter space was completely transparent to them. So the control abstraction was controlling a sound with another sound, so voice to sound directly without thinking about the intermediate parameters. I observed also some characteristics during their free exploration of my system. Most of them, they play around with the search radius within the sonic space, as they identified it as the most responsive parameters in order to change the mapping. So the way the instrument responds to the voice is it changed drastically, changing that parameter. Most of them, the 3D maps were much more difficult to use compared to the 2D maps, at least for first-time user. And comparing two maps, one map results to be more easy to use than another map, and the easy or difficulty was not really related to how many parameters a specific map was driving, but the number of points in the map. From the quantitative measurements that I took during the use case, I got good results in terms of stability of over the postures, so non-variant parameters over vocal postures. I got a very good coverage of both the sonic space and the gestural output space, while repeating specific trajectories into the sonic space was a bit more troublesome, at least for 50% of the participants. But in general, I got repeatable trend in the sonic space and also in the gestural controller output space. I further developed my system to be able to use it in live performances. So as every interface for musical application is supposed to be, I work on it to make it low latency, bug-free, very robust, and capable to run in real time. And in particular, I also have the capability to reconfigure the interface in a few hundred milliseconds, so I can change the instrument that I'm controlling. When I perform with this system, so I can control different instruments. And I developed also this small device that so I call it a burst controller, that I wear it on my burst, to which I can select the instrument that I'm currently controlling, change different setting of the mapping, and I have also visual feedback on it, so I can see the status of the system and the output of the gestural controller space. I perform in a variety of places, in several places, especially this year, and one of the performances was at the Margaret Gutman musical instrument competition hosted at Georgia Tech, to which I was selected this year as a semi-finalist. So I'll conclude this presentation talking about the contribution, the impact, and the future work. So the contribution of these theses are a procedure to learn how to extract robust and continuous data from specific performer voice example, which are representative of the control intention, optimizing the computation towards the minimization of the noise and the accentuation of the gestural, of the spatial aspect of the gesture. The gestural controller, based on the modified version of the self-organizing map. The framework to analyze any given deterministic digital musical instrument, whether this instrument is either a sound synthesizer or a sound effect. Then the mapping methodology to minimize the dimensionality control, the dimensionality of the control space of any digital musical instrument to retrieve discontinuity-free parameters from the reduced sound map. And then the overall strategy to implement this voice to instrument interaction. So the dual layer generative strategy to map across heterogeneous space, used to transform gesture in the vocal space into trajectories into the instrument sonic space, providing linear perceptual response and topological coherence. And finally, the open source proof of concept prototype that expose to the user several intermediate settings and options for experimenting different system configuration. So I conclude that the voice control interface for digital musical instrument is an unsupervised framework to implement generative mappings between voice and DMI. It minimizes the user involvement in the system setup, but at the same time, it maximizes the breadth of explorable sonic space over a set of instrument real-valued parameters. It constitutes an extension to generative interface to effectively perform hands-free musical control tasks. And finally, the impact. The gestural controller and the mapping methodology can be taken out from my system and plugged into any other interface. They don't necessarily need to stick to the abstraction of voice control. And they can also be taken apart. So the gestural controller doesn't need the mapping section to exist. They can exist independently. The open source prototype can be used by other researchers or students to further improve this methodology or to explore different applications. The additional control layers can be beneficial for performers because it's always good to have extra control dimension to promote the creativity and the virtuosities in live performances. And then probably this approach to have a low latency, hands-free control of continuous quantity, multiple continuous quantity driven by non-verbal voice can be used also in other HCI fields. Future work, there's something that can be done in terms of the development to improve my system, in particular integrating everything within a single framework, improve the graphic of the visual feedback, simplify the GUI, and integrate existing technique to reduce the noise and the feedback that are captured by the microphone. In terms of research, I think it will be interesting to explore how to use together different voice acquisition system, so using traditional microphone together with neck microphone and probably other sensors. Also defining a way to defining automatically which is the most proper DMI mode to run the instrument analysis. That at the moment is still a manual selection. Then I think it's interesting to understand how an unsupervised mapping can fulfill what are the user expectations. And finally, it's interesting also to work in the direction of making interfaces adaptive, musical interface adaptive to the user, but without a prior training stage. So making this adaptation gradual and transparent to the user over time. And finally, for this work, I would like to acknowledge my supervisor, Professor Lance Weiss, the Thesis Advisory Committee member, Professor Roger Zimmerman and Mandar Chitre, the Thesis examiners, the NGS executive and staff, my colleague at NUS NCA Lab, MMA Lab, Altman Roma Advanced DSP Group, Tor Vergata DSP VLSI Lab, all the people I met at NIME ICMC, and the participants in the user study, and finally my family and my friends. Thank you.